very exclusive audience. So I just trying to start talking that some people will come around. Okay, so my name is Stefan Nagel. I'm working for the ChargeByte company. And what we do is, at least we try to simplify charging communication. So for the outline, I can also check that. So for the outline, we'll have a brief company overview. And then first of all, what we do is we're getting a bit in the technical area. So we're going to the principles of charging communication for low-level communication and for high-level communication. And then we make the link to our products. And on the end, we were just taking an outlook about our next development steps we will do. So let's start first with a commercial, so to say. So ChargeByte is a German company located at 4 sites. So headquarters is in Leipzig, and there's the production. Myself, I'm sitting in Ulm, and then we have something in Munich and something in Brunswick. And since last month, we also have something in South Carolina. So we are open up a facility in the States. And we do products for charging communication that works on the vehicle side and on the charging station side, which is something special in that company, or in that field, so to say. And this is something we want to take a look now. So if you take a look at charging interfaces, actually most often you see these five different interfaces, and say it's not so different. In Europe, you see here the Type 2, AC Type 2, with three phases where the current draws. PE, PP, CP, and that's it, and a neutral phase. And you can extend this for DC, Type 2, then you just have here the DC plus and DC minus. This is completely Europe, mostly Europe, India also. The Type 1, this is something you have in the States, United States. They have almost the same interface. It's mechanical, different. But they just use one phase, and so that they're using one phase, it looks a bit different, but it's not that different. And they also have, as an extension, the DC Type 1. And specialty in the US, here they have the NACS, which is the Tesla standard, which has here DC plus and DC minus for DC charging, and the same connectors are working for AC charging in the States. But they just have a States, so right now they're struggling if they want in the States Type 1 or NACS. Luckily for us, we don't care about that, because we're just doing communication between the station and the vehicle, and the communication itself always runs over the CP line. And the CP is the same for everything. You have the CP here, you have it here, you have it in Type 1 here, and also for the Tesla, you have the CP here. And it's always the same on the electrical side. On the mechanical side, not, but electrical side, software side, logical side, it's the same. Okay, so first, very basic. How is this working? Actually, you just need 2 signals, 2 informations from charging station to vehicle, and vice versa to setting up a charging station in a very basic AC situation. And the first is that the EV has to communicate to the EVSE. First, I'm connected, plug is connected, and second, I'm now ready to charge. With these 2 informations, you can charge. And vice versa, the charging station has to send to the vehicle, okay, I'm also ready to charge, and this is the amount of current you can draw from me. And this is done with a very simple protocol. So we're doing that here over the CP line. You see it here, I draw it on. And if you just measure with a multimeter on the CP line, then you see just 12 volt, steady 12 volt. And as soon as a vehicle plugs in, it drops down to 9 volt. This is driven by a passive resistance. And it means the charging station just measuring the 12 volt, it sees it decreases to 9 volt, and then sees, okay, somebody plugged in. pretty easy. And from that point on, if the charging station is ready, it starts toggling this PWM. And on that PWM, you have two information. First, if you start that, you see, okay, charging station is now ready to give the current. And second information is the amount of current you can draw. You can just calculate this regarding to the duty cycle. And this is now everything the vehicle needs. And now the vehicle signals, if it's ready, it drops further from 9 volt to 6 volt, which is state C. This is again measured back by the charging station. And then you can charge. This is where the current is flowing. And then it's going vice versa, and it's going back. Well, that's pretty simple, basic AC charging. So you can implement this on a little Arduino, little controller. So this is very easy to do. The question is, if it gets a bit harder, is easy example is DC charging, but also maybe you want to do AC charging with more information and you want to transfer more information. Then you are not getting along with these two signals. For DC charging, for example, you need the state of charge, which has to send from the vehicle to the charging station. You have the max limits the vehicle can do in current and voltage. You have also to signal if the high voltage system is ready from the vehicle. In the charging session, you have to transmit the target values, which is the actual current the target wants to have, which is the voltage that the vehicle wants to have, and if you're ready. And on the other side, also the charging station has to send its max limits, its minimum limits, the isolation status, because then for DC status you have to do a cable check, an isolation check, and also the actual values. And you see this is now too much for little PWM and amplitude modulation. So what we do actually is we are putting here, we are putting here the duty cycle on 5%, and 5% is the signal for the charging station, and for the vehicle we will not communicate on high-level communication. We will now do digital information. And then what we do is we are modulating a signal on this. You see this little noise? When you zoom in such a 5%, you see that little noise, which I measured with an oscilloscope. That's the power line signal. So it looks a bit like noise, but that's the signal we are communicating over. It's a 30 megahertz signal. It's a bit like a radio frequency signal, OFDM signal, on power line communication. And actually, this power line communication is exactly the same as you might have at home, as your Devolo adapter or D-Link adapter, something like that. It's completely the same. Only difference is, at home it goes over your main power, and here it is called power line, but it's just going over the CP line. And we're just doing that because every vehicle has a CP line. Some vehicles only has AC, some only has DC, but the CP line is the same for every vehicle. This is why we are communicating over the CP line. And then when we are setting up such a DC charging session, then we go over different sessions. So it's not completely easy. So first, what we do is we have to setting up the power line for an ISO2 communication, that we at least have a MAC address we can communicate to, and that we can set up as a UDP session, something like that. After you have that, you can send UDP, but still you have to set up a TCP, so higher layer protocol. Layer 3 is TCP, or you do TLS on that direction. If you have that on this layer, then you have a TCP/IP connection. Then you're pretty good. Then it's like you adapt Ethernet or something like that. On that point, you have TCP/IP. And then with TCP/IP, what you do is you're doing these service application protocol, where you check, where the vehicle is checking which applications and application protocols the charging station is providing. Is it DIN? Is it at ISO 1511.2.20? It's a Tesla protocol. Is it a Tesla? And then they're choosing which protocol we're going on. And then the protocols are relatively similar. Then we are starting a session, handing over a session ID that you know on which session you are. On that session, then we check which energy transfer we do, which payment information. Is it AC? Is it DC? Is it payment via plug and charge? Is it payment via an external identification and the authentication? Then we do the compatibility check with the parameters. This is needed, for example, if you have a Porsche 800 volt, or if you have an electric truck with 800 volts and you drive to a charging station with 400 volts, then you can set up the whole session until that point. And on that point, the vehicle will say, okay, I need a minimum of 820 volts to charge me. And the charging station says, maximum is 420 on my side. And then it will fail. And then you can unplug and try your luck at the next charging station at an 800 volt system. After you do the checks, then you do the cable check to see if the isolation is pretty fine. Then you're pre-charging your system. Charging station is pre-charging the system on your target voltage. And if you did that, then you can start with the current demands. So the high voltage switches are clicking, and then current is drawn, and then you can charge. And after that, you can job start and pause charge and re-enable again. But that's the basic stuff you have to go. And if you take a look, then what's behind that? So this is a charging session I measured on I guess it's an Opel Ampero, something like that. And you see here the trace that you see on a TCP/IP with a Wireshark. And actually what you see on the Wireshark is the information we talked about. You see here the EV ready, or it's a bit, the resolution is if I'm that close, the resolution is not so good, but you see better. So you see that the EV ready is actually working. You see the target current you want to have. In this, it's 75 amps. You want to see the target voltage that comes from the vehicle is 450 volts. And all these information that you see here in this XML style encoded are now placed in this, you see it in blue here, in this binary representation. And that's an XE encoder. So what you do is you put in XE, XML, and what you get out is an encoding, a bit encoding, which all these information are shrinked to a pretty small size. And this is what we send then in a TCP/IP protocol, and in an IP protocol, actually. And that's it. If you did that, then you're able to charge. Okay. Now let's take a look what we do here. So actually, if you think about what I mentioned, then you can split all the parts in three components. You have the basic communication, which is power line, physical layer, maybe layer 1, 2. Then you have your V2G that you saw with the XE encoding, and you need a complete controller to handle all that. And this is where our products come in place. So for the power line communication, for example, we are having power line stamps. So this is some kind of power line stamps. It has now a vertex COM on it. We're also shipping that with a Qualcomm, with a QCA. And you interface that via SPI. It's relatively easy. On the other side, you have then a high frequency power line signal. And we're taking care of that this is fairly flashed, that it's calibrated, that the spectrum mask is not overgoing, that you have a smooth spectrum mask and a flat spectrum mask, and no noise on that. And if you have that, then you can communicate over power line, okay? But still, what you don't have, just as a reminder, so this was the power line, this little ripple. But still, you can communicate over power line, but what you not have is the V2G communication. And for that, actually, you saw the chip I had on the first slide. This is all the power line section. And then we had just placed a controller next to it. And the controller is then handling the TCP/IP and all the V2G stuff I talked about. So actually, then here on the output is then power line communication, high frequency. And here on the input, you're just sending CAN signals. You're just sending, I want to have that current, I want to have that voltage, and the module is then doing the rest for you. And you see, so it's the same hardware for vehicle side and for charging station side, just do two different flashwares, where we're doing also the CP handling and where we implemented and compromised and optimized the library we are doing, that everything is running on such a little NXP processor. And then it looks roughly like this. So this is also a trace that we checked via CAN. This is now the CAN trace. This is what you see if you look on the CAN line where we communicate to our modules. Then you see, for example, our state machine state in blue. And here's the state machine state. In here you have the state of charge, the present voltage, and the present current. And you see, state machine is starting at default, goes up to the initialization. Then we are here in the isolation check. We are here in the pre-charge. In the pre-charge, you see now the voltage is rising up until you have reached 360 volts. In the charging session, now the current is going up from 0 to, I guess it's 40, 50, yeah, 30, 40 amps. And then here you charge with 30, 40 amps, and the vehicle goes then back the state of charge, which is, yeah, 60%, something like that. And this is what we try to do. So we try to have it in this area where actually everybody can understand from this, which is not so easy. So this is a bit of the hard work. This is what we do in software. This is the level we are. And we try to simplify that to that level, which actually is then pretty easy. But still, if you're on that level, you still have to integrate that module in anything and communicate with that. So the third level of integration, so to say, is that you're not solar anymore, but you're adding a complete ECU. And now you see, now you have different hardwares. Now we cannot use the same hardware for vehicle and for the charging station. Now for the vehicle, we have then an ECU, which is right now built in electric trucks and buses and something like that. And this is, for example, our AC charge controller, which is, with that you can build up your charging station. So a colleague of mine has that in his garage, and it's everything he needs. Just a switch, that's it. On the left side, so the automotive side, this is then built according to functional safety. This is automotive grade. This is then qualified to be on the road. It has a road approval that you can directly place it in a vehicle or in a truck. And on this side, we are working a lot on Linux systems, and we are working a lot on open source systems. So if you purchase that, Charge Control C, it comes directly with Everest, which is an open source implementation of the stuff I showed you. So actually, we have two types of firmware. We have one firmware as an Archer system. This is closed source because we are putting a lot of effort to optimize that and to bring that in very small size. And we have an open source implementation, and you can just check that out on Everest. It's a project funded by the Linux Foundation on the energy point, and everything that is implemented is pretty free. And this runs on our platform. So either you can build up your own platform, you can use our modules with the platform if you have difficulties with Powerline, or you can use that. And due to the fact that we are here pretty free and that it's open source, we also implement other software stacks like Switch, Joseph. So they are coming up with an OCPP 201 implementation. So you can have that platform actually with every software you want to have. here is a conclusion. So this is what we understand in simplifying charging communication. If you are actually a software company and you have an idea how V2G is working, but if you struggle a bit with powerline, then you can just integrate powerline chips and use these powerline chips. If you're struggling with all the V2G communication, then you can just purchase a bit bigger chip, a module with a controller, and just interface it via CAN and handle the ISO 578 and DIN 7121. And again, if you directly want to integrate a complete controller, then you can also do that. So we try here to be actually on every level. Okay, so what's going on in our newest development? So everybody talks about the .20 implementations. We have first testing sessions, we have first implementations. It's not serious ready, but we are heavily working on that. And just to let you know, .20, the big issue in .20 is the bidirectional power transport, that you can charge but also discharge your vehicle. This is one of the biggest sites here. We are doing this on the Linux side, open source, so you can check that out in Everest. But we're also doing this closed source for our RTOS machines. And we're doing this for both sides, EV side and EVS side. Then we are now doing charge cores. So what we do actually, you see it here. Actually, what we did is we take these modules, which are pretty popular in the meantime, and we are adding a bit more. We are adding a bit more features in it. So we are adding here an ESP32, which is a cheaper chip, but also has more processing power. And we are doing then here also OCPP, and we're having then a lot here and have then a complete charge controller that you can just integrate. This is called a charge core. And we're doing here the same, but just with a Linux core, an IMX93, so that you can just integrate that and place your own stuff on that. And for doing that, we're also adding a little co-controller for functional safety. You don't see that right now so much in charging stations, but it will come. So it's just a matter of time. Functional safety and security. And this is what we're doing right now very heavily on the automotive side. If you are releasing now a new car, it has to be handled with functional security, with security features. This is what we do right now, that you're securing up your diagnosis, securing up your flashing system, and securing up the whole communication between the different processors, and have here encrypted communication. Okay? That's it. I hope you enjoyed the talk, and I hope you enjoy the day here at the trade fair.